All right, Kelly, that's me. I'll share my
Manish
screen.
Kumar. Professor Kumar has been at the University of Cincinnati, uh, other than a small period where he was in Toledo for a while. He's been in Cincinnati since 2007. He's the graduate director and also the co-director of mechanical engineering and mechanical and materials engineering here at the University of Cincinnati, and the co-director of the Industry 4.0, 5.0 Institute. Uh, he's very well known across the university, a close friend, and a very strong collaborator. Manish, take it away.
Thank you so much, Kelly. As Kelly mentioned, I have the pleasure and honor of working with Kelly for 17 years, and together we have over 60, 70 papers that we have co-authored together. Many of them on fuzzy logic. And this paper that I'm going to talk about is also uses fuzzy logic. But before I start talking about that, I would like to thank Kelly and other organizers of this webinar for the chance to talk about this paper. Let me share my screen here. And can you all see my screen?
Yep.
Very good, Manish. Go ahead.
All right. Thank you so much. So the title of this paper is Active Manipulation of a Tethered Drone Using Explainable AI. This is a work carried out by my previous Ph.D. student, Dr. Shraddha Bardavkar, who is a postdoctoral researcher now at University of Maryland. This work is kind of an offshoot of the work that C did for her PhD, which involved developing controls for multiple UAVs carrying a common payload. And when she was doing that, she was looking at modality of obtaining a force feedback um, from the interactions between multiple drones to be able to carry out the collaborative work of lifting a common payload. And based on that, we were at that time also we were working on a tethered drone project for Ohio Department of Transportation. And as you know, tethered drone does offer a lot of advantages, mostly in terms of continued operation for longer time, but also, cable can be used to transfer data, as well as cable also provides a way, a safer mechanism for operating drones. But when we were working for ODOT, one of the limitations that we saw firsthand was that the ground station for the tethered drone needed to be stationary. You cannot move that, and a lot of times, if you need to gather data at a slightly different location, you needed to bring the drone back on the ground, move the ground station, and then fly the drone again, and which was a cumbersome operation, and a lot of time was wasted on that. Uh, and at that time, use of the force feedback for collaborative drone, we were working on that, and then we said, why not use the same concept here in developing this technology of actively tethered drone. What you see over here is a very interesting use case of attaching the drone to a ground vehicle, ground robot, rover. In this case, this is the Martian rover, and the Martian helicopter. And since Mars doesn't have any um, obstacles, it's a very interesting use case where drone could be attached to the rover, and obtain the power from rover to have a longer operation. But when we look at there are some work done in developing controls for this. Major challenge over here is that when you attach the drone to ground vehicle via tether, tether can provide destabilizing force on the drone, and drone might crash. This tether is not only supposed to provide a way to guide the drone, but also we need to make sure that it does not destabilize the drone. So drone controller needed to be compliant in nature, so that if it is pulled, instead of resisting, you comply with the force. So the idea is that as the rover moves, the drone follows that using the tether force. So we are using a force torque sensor, and in this setup, since you're using force torque sensor, you do not really need to have any positional feedback needed. Because you just follow based on the force cues, force and torque cues. In this case, just force cues, and so you do not need to have any positional feedback. So that's an added advantage for operations in GPS denied environment. But when it comes to developing these types of drones, the work that is mostly done made use of position feedback. So you have position known for both the drone as well as the rover, and you develop a controller that maintains relative position of the drone at a stable distance. Over here in our paper, we developed this controller that provides this compliant mechanism for following rover using the force cues. We develop a fuzzy logic scheme for doing that. And the fuzzy logic, of course, provides several advantages, particularly for use in here. And of course, we can develop this kind of compliant mechanism just by thinking about the heuristics involved over here. So that gives an advantage of using human expertise in control design. Explainability, which is the topic of this special issue, is certainly maintained here because of the rules and membership functions. You can really explain why drone is taking any decision based on the inputs that is provided to it. Also, fuzzy logic is able to deal with a lot of noise and uncertainties. Now, apart from this, one of challenges that we have in this kind of a tethered drone operation is that of wind disturbances. So because wind disturbance can affect the force torque reading, force sensors reading, it becomes less reliable to rely on force sensor if you're operating in a windy situation. So we developed an adaptive controller to estimate the wind disturbances, which can be then used in this kind of force-based control. Going on the dynamics over here, I will quickly go through this. You have the rover here attached to the drone via this string, which is tight. And so you have forces acting here due to tension in the string, and that is used as a force feedback force sensor attached here in this situation. So you get the tension as a measurement, and you write down these equations based on free body diagram, and then based on that you can write down the equations of motion as shown over here. Now, in this scenario, we are considering two control inputs. One is the desired pitch angle and then desired yaw angle. So these are the two inputs to the drone. And we are obtaining these values using fuzzy logic as well as adaptive control schemes, as we'll see. So in case of wind disturbances, we formulate the problem within adaptive control theory. So you write down the equations of motion in this format. Again, consider the force due to wind for at any arbitrary velocity. You write down these equations of motion, and then you consider a stabilizing input as as shown over here, and where your S naught is the error between the velocity, actual and the reference velocity, and then similarly you write down the equations of motion for the ground robot, the rover, and in this case we assume a simple PD controller for the drone for the rover, because we are not developing a controller for the rover in this paper. We assumed something that robot controller is perfect, so it applies the desired force that is needed from the controller. So the desired tension can also be written in this form, and based on that we write down the Lyapunov candidate Lyapunov function, and then prove that the Lyapunov function will be bounded, and then using Barablat's lemma you also show that the error for both the robot as well as the ground robot, which is this one, and the drone converges to 0. And similarly for fuzzy logic, we are considering two inputs. One is this the difference between the measured force and the tension, the equilibrium tension that you want in the tether, and the rate of change of this force, the measured force, to obtain the desired angle, pitch angle, and then desired yaw angle. And typical fuzzy rule, which is derived from essentially looking at how would human expertise be implemented. For example, if your tether is pulling in one direction and the rate of change of that force is large, then you move fast in the same direction. So using that kind of logic, we wrote down this fuzzy rule base, and using 5 membership functions. And what you see over here is the control surface. So these are some of the results over here. This is the angle, the tether angle that you see, the desired and actual converges. Likewise, the tension converges to desired value. For this is all simulation. This shows the fuzzy control input, which is force and force dot, and how the fuzzy output behaves with respect to the inputs over here for both the controller for desired pitch and desired yaw. And more results. There's some simulations over here showing how this the drone and the rover collaborate. So now these are the results for wind disturbance analysis. Over here, a constant wind is applied. In our derivation, we are assuming the wind disturbance is constant or very slowly varying, and these are the results that show very, very nice and smooth convergence for for the position of the ground robot and the drone, how it converges to the desired values. And this shows how we are estimating the wind forces in X and Y direction, which also, so this is the simulation setup. You have wind forces acting in both X and Y directions, and which is estimated over here. Additionally, we did some experiments, and it was interesting. We used, Crazy Fly 2.1 attached to a Turtlebot 3. And if you know this Crazy Fly, this is a very pretty small drone. And it's so small that it doesn't have the capacity to even hold force torque sensor. But luckily, since this is a massless string, any force measured on the ground robot would be same as on the other end. So with that assumption, we put sensor on the ground robot and use that value to carry out this. These are some of the results. Pitch and fuzzy yaw results, and how it converges to desired commanded values. This is another of the experiments in which it's following the drone, which is moving in a circle, which is a much harder experiment because your direction is changing continuously. And these are some of the results for that. And I'm running out of time, so I'll quickly wrap it up. These are conclusions. We are using force feedback to provide effective control strategy. And we used fuzzy logic for doing that, and also introduced adaptive control that estimated wind disturbances. And we also demonstrated the simulation to real experiments capability with minimum change in control parameters for fuzzy logic. So we'd like to acknowledge the fellowship that Dr. Bardavkar received from SRIDE. Professor Cohen has been kind enough to provide his inputs at times, and Charles Dorn is director of the SRIDE. And so we have a patent application based on this work here. I will stop my presentation and invite any questions that you might have.
Yes, we have time for just one question. If there is, anybody raise your hand from the attendee list. I don't see any raised hand. If not, then thank you very much, Manish. We'll go over to our next presenter. Oh, Barnabash has raised his hand.
Just a
Barnabash,
quick
please
question.
go ahead.
Just a quick question. So, as far as I understand, you had the system based on human expert based rules. Did you try any training or adjusting the rules based on the results?
Yeah, so we did do that, but not using any kind of algorithm, but by manual tuning of the parameters.
Yeah, thank you.
Thank you.